How silver is liberated, from ore to pure metal. Your grandfather probably had a change jar, maybe a coffee can on a shelf in the garage. And if he was born before 1965, some of those coins were not just money, they were silver, real silver.
Welcome to Secrets of Everyday Things, the channel where everyday secrets are uncovered and explained.
Here is what nobody tells you about silver. It is not made. You cannot manufacture it, synthesize it, or grow it in a lab. It is an element, number 47 on the periodic table, and it has been locked inside rock for hundreds of millions of years. What we do, what engineers and metallurgists have spent 3,000 years perfecting, is liberate it. And the process that frees silver from stone is stranger, older, and more counterintuitive than anything you would expect. Picture Virginia City, Nevada, 1859. A prospector named Henry Comstock is arguing with his partners because a thick, sticky blue mud keeps clogging their mining equipment. He wants the mud gone. His partners want gold, and they are finding traces of it. But this mud is constantly in the way. So they sent a sample to an assayer in San Francisco. The result? Over $3,000 worth of silver per ton. In today's purchasing power, that figure is eye-watering. The blue mud they had been cursing and tossing aside was almost pure silver sulfide. The Comstock Lode, as it became known, sparked the largest silver rush in American history, flooded the treasury with silver dollars, and financed the infrastructure of the entire American West. It started because someone was annoyed by mud. Here is the thing about silver that most people do not realize. It almost never shows up on its own. Silver is vanishingly rare in the Earth's crust, averaging 0.07 parts per million. To put that in terms you can picture, imagine taking every grain of rock and soil on Earth's surface and spreading it into a single pile. Silver would account for 7 grains out of every 100 million. You would need a sieve finer than a human hair to find it, and it does not hide where you would expect. Most people imagine silver miners tunneling into dedicated silver veins, pulling out gleaming ore. The reality is stranger. About 75 to 80% of all silver mined each year comes out as a byproduct. A passenger inside copper mines, lead mines, and zinc mines. Silver was not the point. Silver just came along for the ride. The ore itself is another surprise. When silver concentrates in nature, it tends to lock itself inside specific minerals. The most common is galena, a lead sulfide ore so dense it looks like shards of metallic mirror. Another is argentiferous galena, meaning silver-bearing lead ore, where a tiny fraction of silver threads through rock that looks, on the surface, completely unremarkable. In argentiferous galena, the silver fraction can be as low as 1% of total ore mass. But silver is currently 364 times more valuable than lead by weight. That 1% is everything. So before a single ounce of silver reaches your electronics, your silverware, or your solar panels, it has to be hunted through hundreds of thousands of tons of ordinary rock. And that hunt requires chemistry that took humans centuries to figure out. The first step in separating silver from crushed ore is something called froth flotation. And here is what nobody tells you about this process. It is not really a chemical separation. It is a physical trick played on the surface tension of water. Crushed ore gets fed into enormous tanks filled with water. Engineers add a chemical called a xanthate collector, an organosulfur compound that finds silver mineral particles and latches onto them. Once latched, it flips the particle's surface property from hydrophilic, meaning water-loving, to hydrophobic, meaning water-hating. Compressed air is then pumped in at the bottom, creating millions of tiny bubbles. The silver particles, now coated in xanthate and repelling water, stick to those bubbles. They float to the surface in a mineralized froth. Everything else, the waste rock, the material with no value, sinks. This process, from raw, crushed ore to silver-rich concentrate, typically runs 4 to 12 hours per batch. At the Core Rochester mine in Nevada, the largest active silver mine in the United States, it runs continuously. 24 hours a day, 365 days a year. And the woman who first worked out the core principle behind it was a Denver homemaker. In 1886, Carrie Everson patented a process using oil, acid, and salt to separate sulfide minerals from waste rock. Nobody in the industry took her seriously at the time, but the insight she described, that minerals could be separated by selectively manipulating their surface behavior in water, became the conceptual foundation for modern froth flotation. She is now called the mother of the process. Froth flotation only gets you so far. The concentrate it produces is rich, but not pure. Silver is still locked inside sulfide minerals alongside copper, lead, zinc, and traces of other metals. To go further, you need to dissolve the silver completely out of the mineral matrix. Enter cyanide leaching. In large slurry tanks, the flotation concentrate is mixed with a dilute sodium cyanide solution. Cyanide is extremely selective. In the presence of oxygen, it forms a stable complex with silver and gold, pulling them out of the mineral in dissolved form. Everything else stays behind. The result is a liquid called pregnant solution, loaded with dissolved silver. And this is where it stops making sense. The next step requires something deeply counterintuitive. You have to remove the oxygen, not add it, not manage it. Remove every last molecule of dissolved oxygen from the solution before you proceed. Oxygen is the villain here. Left in the solution, it attacks the zinc dust used in the next recovery step. It coats each zinc particle with a passive shell of zinc oxide, rendering it chemically inert. The zinc dust stops reacting. The silver stays dissolved. Your extraction fails. In the early days of cyanide leaching, around 1900, this was a chronic and baffling problem. Engineers kept getting incomplete recovery. Silver they knew was there, dissolved, measurable, provably present in the liquid, simply was not precipitating. Nobody was quite sure why. The answer, when it finally came, did not come from a chemist working through theory. It came from a man watching bubbles. In 1916, a metallurgist named Merrill-Crowe was studying the behavior of pregnant silver solution after zinc dust was added. He noticed something. Tanks with better silver recovery had fewer bubbles rising through them. Tanks with poor recovery were almost sparkling, like carbonated water. More bubbles, less silver. Dissolved oxygen, he realized, was behaving exactly like carbonation. Invisible, odorless, completely measurable once you knew to look for it. And it was quietly killing the zinc dust before it could do its job. His fix was elegantly simple. Run the pregnant solution through a vacuum tower before adding zinc dust. The drop in pressure forces dissolved gases, including oxygen, out of the liquid before it touches the zinc. The zinc stays reactive. Silver precipitates cleanly, rapidly, completely. This is the Merrill-Crowe process. Still used today, unchanged in principle, in virtually every major silver and gold mine operating on Earth. Merrill-Crowe solved one of the industry's most stubborn problems by watching bubbles. Recovery rates improved by nearly 40%. Not because the chemistry changed, not because the ore changed, because one man noticed something invisible was in the way and found a method to pull it out before it caused any damage. After Merrill-Crowe precipitation, you have what is called silver mud, a wet paste of silver mixed with zinc and residual impurities. This goes through retorting, where heat drives off the zinc as vapor, leaving behind rough silver bars called doré bullion, typically 90 to 95% pure silver. But that is not pure enough for most industrial applications. The doré bars go to a silver refinery, where they are dissolved in hot nitric acid. And here is where the engineering gets serious. The reaction of silver with concentrated nitric acid is violent. It produces nitrogen dioxide gas, brown, acrid, toxic. At high concentrations, nitrogen dioxide causes chemical burns to lung tissue within seconds. Modern refineries are built around this one reaction. Every vessel is sealed, every vent is scrubbed, every release is neutralized before it reaches the air. The fume scrubbers are not optional extras. They exist because early refineries did not have them, and people died. The dissolved silver solution is then processed electrolytically. Pure silver deposits at the cathode. The anode, cast from impure silver bullion, slowly dissolves. Trace amounts of platinum, gold, and palladium hidden inside the original door drift to the bottom of the cell as a sludge called anode slime. This sludge is collected separately and refined to recover those precious metals as a secondary yield. What comes out at the end is silver at 99.9% purity. A single grain of this material, 0.05 of a troy ounce, can be drawn into 122 meters of wire. That is roughly the length of a football field from end zone to end zone, plus most of a city block on top of that. I need you to stop and sit with this for a moment. Everything you just heard, the open pit blasting, the froth flotation, the cyanide tanks, the vacuum towers, the nitric acid, the electrolytic cells, all of it produces a raw material that the modern world is consuming faster than it can be replaced. Every new megawatt of solar photovoltaic capacity installed anywhere on Earth requires 25 to 30 kilograms of silver, incorporated into conductive paste printed across the surface of each solar cell. Advanced heterojunction panels use even more, up to 22 milligrams of silver per watt, a 50% increase over older designs. As the world installs more solar capacity to power a cleaner future, it needs more silver to do it. At current production and consumption rates, geologists estimate that known extractable silver reserves may last approximately 20 years. 20 years. That is not a forecast. That is a countdown. The United States gets a close-up view of this. Nevada's Coeur Rochester mine is currently the largest operating silver mine in the country. Idaho's Silver Valley, the Coeur d'Alene district, has produced more silver than almost anywhere else in American history. And across the solar-heavy states of the Southwest, every panel going up represents another 25 to 30 kilograms of silver drawn from a reserve that is not growing back. The same metal Comstock's miners once cursed as useless blue mud is now, ounce for ounce, one of the most strategically critical materials on Earth. Go back to that change jar on your grandfather's shelf. The silver dimes, the walking Liberty halves, the pre-1965 quarters pulled from circulation when their metal value outpaced their face value. Those coins disappeared from American pockets not because silver was forgotten. They disappeared because silver became too valuable to casually spend. That is still true. It always was. Silver is not gold. Silver is not platinum. Silver is element 47, the best electrical conductor known to science. A product of 3,000 years of metallurgy and a century of hard-won chemistry. A witness to the Comstock Lode, the Apollo program, and now the solar revolution. Not gold, not platinum, but silver. The most extraordinary things are hiding inside the most ordinary. And the next time you hold a smartphone, flip a light switch, or look at a solar panel on a neighbor's roof, you are looking at something that started as blue mud in a Nevada mine. But silver does not travel alone. Hiding inside every batch of anode slime we just described, there is a family of metals so rare they are measured in parts per billion, worth more per ounce than gold, and almost nobody outside the industry knows they are there. Next time, we are going to follow that trail into one of the strangest corners of industrial chemistry on Earth. And now I want to ask you something. Do you have any items made of silver at home? Or have you ever owned an old silver coin? Let me know in the comments.